Yeah, good morning, students. Last class we have discussed different classes of pericyclic reaction. In today's class we will be discussing molecular orbital theory. Yes, molecular orbital theory. You heard it correct. Molecular orbital theory. You are already familiar actually. Yeah. Now with respect or in terms of pericyclic reactions, how the molecular orbital theory is helping us, that we are going to study in today's topic. Yeah, molecular orbital theory, it tells you about HOMO, LUMO, the ground state electronic configuration, the excited state configuration of pi molecular orbitals. HOMO and LUMO is also its information is also being given by molecular orbital theory. This already the molecular orbital theory concept you are familiar. According to linear combination of atomic orbitals, mixing of p atomic orbitals produces pi molecular orbitals. That means atomic orbitals upon linear combination will produce molecular orbitals. And the second point what I have mentioned is number of p atomic orbitals mixed is equal to number of pi molecular orbitals. That means if n number of p atomic orbitals are mixed, then you will result in n number of pi molecular orbitals. Right, now after the linear combination of atomic orbitals, the pi molecular orbitals that are being produced, now what is its nature? The bonding and anti-bonding molecular orbitals. So what is the percentage of bonding and what is the percentage of anti-bonding molecular orbitals? The formula, if n is equal to even, then you will have n by 2 percentage of bonding molecular orbitals and you have n by 2 percentage of anti-bonding molecular orbitals. That means 50% you'll have of anti-bonding molecular orbitals and 50% you'll have of bonding molecular orbitals. This is when if n is equal to even. If n is equal to odd, then you will have n minus 1 by 2 number of bonding molecular orbitals, 1 non-bonding molecular orbital and n minus 1 by 2 percentage of anti-bonding molecular orbitals. Here I have taken example that 3 atomic orbitals upon linear combination of atomic orbitals will result in 1 bonding molecular orbital, 1 non-bonding molecular orbital and 1 anti-bonding molecular orbital. Now energy wise, if you go, I have mentioned the sequence here. If on y-axis you take the energy, then you will have the least energetic is bonding molecular orbital, followed by non-bonding molecular orbital, followed by anti-bonding molecular orbital. So least is bonding molecular orbital, the highest is anti-bonding molecular orbital and intermediate is non-bonding molecular orbital. The energy of non-bonding molecular orbital is comparable to that of atomic orbitals energy. Yeah, next, the molecular orbitals. Once upon linear combination of atomic orbitals, the molecular orbitals that are produced, right, they can accommodate 2 electrons, right? Yeah, this concept you are already familiar. Next, molecular orbitals are filled according to Aufbau's principle. Aufbau's principle also you are familiar. What is it? That the energies, the electrons fill low energy orbitals first, right? Then higher energy orbitals are occupied by the electrons. Next is molecular orbitals are designated as psi 1, psi 2, psi 3 till psi n and are arranged in their increasing order of energy, right? Next is number of nodes. Yeah, this is very important in drawing the pi molecular orbitals, right? N number of nodes, the formula to use or to calculate is n minus 1. For example, if you have psi 1 molecular orbital, just now I have told you na, the pi molecular orbitals are designated as psi 1, psi 2 like that. So directly we are referring to the name. Psi 1 nodes is equal to, right, what is the n here? N is equal to 1. So 1 minus 1 is equal to 0. Psi 2 nodes is equal to, right, 2. Here n is equal to 2. So 2 minus 1 is equal to 1. So psi 1 will have 0 number of nodes. Psi 2 molecular orbital will have 1 number of nodes. Likewise, you can calculate depending upon the number of pi molecular orbitals that are present in that particular molecule. Next, the pi molecular orbitals with even number of nodes or 0 nodes possesses the plane of symmetry, right? Therefore they are symmetric with respect to sigma. This explanation you'll have clarity when I draw the pi molecular orbitals and give you an explanation. So you people have familiarity, right? In symmetry topic I have taught you all what is sigma, that is plane of symmetry, and what is C2 symmetry. Sigma is nothing but if you are able to cut the molecule into two equal halves, or if you put a plane in such a way that both the halves are mirror reflection to each other, then it is symmetric with respect to plane of symmetry, or it is that molecule is supposed to possess plane of symmetry, right? Now C2 symmetry is nothing but it is a angle of rotation 180 degrees. If you rotate the molecule by 180 degrees and if you result in an equivalent configuration, then they are symmetric with respect to C2 symmetry. That is what here I have written. Yeah, the pi molecular orbitals with odd number of nodes possesses C2 symmetry. So just you remember that the pi molecular orbitals with even number of nodes possesses plane of symmetry, or 0 nodes possesses plane of symmetry, and the pi molecular orbitals with the odd number of nodes possesses C2 symmetry. So once they possess C2 symmetry, they are symmetric with respect to C2 and anti-symmetric with respect to sigma, right? And then molecular orbitals with electrons having maximum energy are called as HOMO, right? For time being, you just remember what do you mean by HOMO and what is LUMO. HOMO is nothing but highest occupied molecular orbital, and LUMO is nothing but lowest unoccupied molecular orbital. Now HOMO, molecular orbitals with electrons. LUMO is molecular orbitals without electrons. Okay, so you have HOMO will be with electrons, LUMO will be without electrons. So molecular orbitals with electrons having maximum energy are called HOMO. Molecular orbitals without electrons having least energy are called as LUMO. Now symmetry properties of molecular orbitals, that means if they have sigma, then it is said to be symmetric with respect to sigma, right? Yeah, if they have C2 symmetry, then they are said to be symmetric with respect to C2 symmetry, right? Yeah, hopefully it is clear, the video is clear. Yeah, now for example, if you take this pi molecular orbitals, how many pi molecular orbitals? 2 pi molecular orbitals are there. Now what is the configuration? What is it? It is psi 1. It is also called as pi. Now this is pi star. I have taken 2 pi molecular orbitals, right? Pi and pi star. Bonding molecular orbitals, anti-bonding molecular orbitals. So this is designated as psi 1 and this is designated as psi 2. Now if you go for the calculation of number of nodes, right? 1, psi 1, number of n is equal to 1. So 1 minus 1 is equal to 0. So you draw the molecular orbitals in such a way that there are no nodes. So both the shaded lobes of the pi orbitals, right, I have taken it top and the unshaded are taken in the bottom, right? Now once you draw the psi 1 molecular orbitals, right, you just put a plane. If you want to know whether it is symmetric or anti-symmetric with sigma, just try to put a plane, right, and see to it and observe whether this half is a mirror reflection of this half or not, right? For example, if you see the shaded here is getting reflected here on top, the unshaded is getting reflected unshaded on the bottom. That means it has got sigma. So now you can say that it is symmetric with respect to sigma, right? Once you look for this, yeah, this is pi star psi 2. How many nodes will be there? 2 minus 1 is equal to 1, right? So it has got one node. Now you draw the pi molecular orbitals in such a way that the shaded of one pi molecular orbital is on top and the unshaded is bottom down, right? Likewise, here you would draw the unshaded on top and shaded on bottom. Then only you will have node, right? If both the shaded are on top, you cannot have a node. If they are opposite, then only you can have nodes. So here how many nodes are there? One node. So I have drawn the molecular orbitals, pi molecular orbitals in such a way that it has got one node. Now in order to see whether it is symmetric with respect to sigma, that is plane of symmetry, you just try to put a plane, right? The plane is perpendicular to the horizontal plane, molecular plane, if it is lying flat, the molecular orbital, if the bimolecular orbitals are lying flat on the plane, and then if you put the plane, this plane on perpendicular axis, then just look for the reflection. Now here the shaded, is it reflecting here? No, it is not reflecting here, so it doesn't have any plane of symmetry. So sigma is absent. Sigma is absent means it is anti-symmetric with respect to sigma. Now likewise, the same psi 1 and psi 2 I have taken for the discussion of C2 symmetry, right? For the discussion of C2 symmetry, whether this is symmetric with respect to C2 axis or not. Here, yeah,